Item B, intrinsic geometry, exterior algebra in 3D. As I said before, we can expand for any dimension, okay? 4-dimensional and so on. So, B Part 1, manifolds. B Part 1, Lecture 11, about the manifold. Obtaining the basis vectors partial with respect to the curvilinear coordinate xi, where in this case for a 3-dimensional, I is 1, 2, or 3. Now, from the previous lecture, lecture 10, the addition derivative, we derived this expression here. Now we'll define the velocity of the curve gamma s. Vj is the ordinary derivative of this coordinate, curvilinear coordinate, with respect to lambda. Remember, xj is, in this case, is curvilinear coordinates. We are focused. But they can be represented by 3 sets of numbers which are the Euclidean coordinates. You see? Now, just substitute the definition over here. So let's go to step 2. Interpret the tangent space and the basis vectors. Now we're going to expand. So the space vector or tangent space TP_M3 at the point P, you see, consists of all possible velocity vectors of smooth curves passing through point P. You see, you can see here, you have, there's a point P, you see, you have all possible vectors. This over here, it is the tangent P M3. You see this all possible vector, okay? So this space over here, the vector space, then can be expanded by this case, okay? The basis vectors, okay? Partial x1, partial x2, partial x3. So this consists of the basis vector, covariant, attention now, covariant, because the index is in the denominator, okay? They belong to the space vector. So that's where you define, okay, the tangent space, okay? Attention now, passing through the point P that belongs to the manifold and also belongs to the space vector, okay? It's common. Now, each velocity, Vj at P, can be written in terms of the base vectors, you see? Now I define d of the lambda as a vector v by definition. So this is Vj partial xj. You see, look at here and look at here. You see, this over here, you see, is defined as a vector v. You look at here and look at there. You see? So if this is applied, to fi, this here, you can compare with this over here, okay? So this applied, it's easy, you see, look, to the fi, you see? From there, I just drop it, fi and fi, and I define the vector v as d of the lambda. I think it's quite clear, okay? So this expression here is this one over here. You just compare. Now, so the set of partial derivatives, you see, forms a natural base for the tangent space. Okay? Now, for higher order dimension, you see, it's the same way. You see, so this will be, for instance, 4-dimensional. You put 4 over here, so I have 4 unit. No, I'm sorry, it's not unit. 4 basis vectors for this case we are analyzing. So thus, the set of partial derivatives, this forms a natural base for this one. Step 3, justification of covariant basis vectors. Those are covariant basis vectors. Why covariant? Because I is in the denominator, okay? As we pointed out on item A, this is item B, okay? We just emphasized, okay, what is covariant and contravariant basis. Now, a justification of this, okay, each base vector represents a local directional derivative along the curvilinear coordinate xi. Don't forget, xi, it is a curvilinear coordinate, okay? That is, it acts on, in this case, on the function s. You see, this partial derivative here acts on the function. If by the attention now, I can use this expression here, define derivative, because these variables, okay, xi, in this case, they are in the tangent plane, okay? This is the approximation. This I insisting, okay, and to focus this, because when I use this, okay, I forget the manifold. I forget the manifold because in the manifold you cannot relate it, xi plus epsilon minus xi. I can't, because as I said previously, there's a labeler point. Okay, you label each point, okay, which doesn't see, okay, the other, your neighbor. You don't see that. But if you approximate to the tangent plane, you see in this case, we can do this difference here. That's clear what I'm saying, you see? Then that's the definition of this. Since xi are local coordinates, okay, in this independent coordinate, okay, the basis vectors are linear independent also. You see, x1, x2, and x3, they are independent. So, by consequence, okay, the partial derivative for I1, 2, 3, they are independent, linearly independent. So I can expand any vector in terms of linear combination of this base over here, okay, on this base over here. Now item 1, 2, 1, 2, and 3. Every smooth vector field in this tangent space can be expressed uniquely as a linear combination of this base vector, confirming they span the space. See? So, as I just said, okay, seconds ago, that I said what is written over here. So I can expand any vector, okay, as a linear combination of this base vector over here. See? Now, conclusion. By analyzing the level curves, attention now, all these here, okay, we initiated using the concept of level curves belong to the manifold. See, that's important to review. Lecture, I think, 9, 10, and 11. So by analyzing the level curves and computing the velocity vectors, we established that the natural base of the tangent space, in this case, consists of the coordinate, in this case, partial derivative. So this is a natural basis vector, covariant basis vector. This vector defines the covariant basis of the tangent space, allowing us to express any tangent vector in terms of these bases. See, that's our conclusion here. Okay? So, in the next lecture, we'll talk about the dual cotangent vector space. See, it will be the next lecture, lecture 12.